Hello everyone. Today we're going to finish 5.4 and this will be the last lesson on 5.4, which of course if this is the last lesson usually deals with real world situations. So today we're going to be dealing with modeling of a polynomial function in a real world situation. So you can see how this is used in our daily lives. And here we go, modeling a polynomial function using real-world situations. So we're going to give you some, just review some pre-knowledge from previous lessons, so that way we can apply it to the real-world problem, because we're going to be dealing with a 3D box. So it's going to be so we need to review the volume of a rectangular prism, which is a box. And the volume is defined by length times width times height. So volume equals length times width times height. So that's a formula that everyone should be very familiar with, because you should have learned the volume of a three-dimensional figure in the past. So here we go. And the first problem is says to create an open top box out of sheet of cardboard that is 9 inches long and 5 inches wide. You can make a square flap of side length x inch in each corner by cutting along one of the flap sides and folding along the other side. So this is kind of like a picture of what it looks like. In the first diagram, a solid line segment in the interior of the rectangle indicates a cut. So solid means cut, dotted means fold. And after you fold up the four sides, you should have something that looks kind of like this. And so we need to actually find the volume of the box by using these dimensions that we know. So after you can visualize, after you fold it up, pretty much the actual length would only be like from here to here. And then the actual width would actually be only from here to here. So if you can think of the new dimension for the box, the total dimension, the total length is 9 inches, but we got to take away these two corners that you call x, right? So it's 9 minus 2x should be the new length. And then the width, same thing. The total is 5, but you're going to minus the two corners that are folded up, which means 2x. So now we've got two dimensions that have changed, but the height should still remain the same, which is just x. So we've got three dimensions. So in a way, if we use the so we got the length, now it's going to be 9 minus 2x, and everyone understands why. And the width, that is going to be 5 minus 2x. And we got the height that did not change is still x. And so since the lengths are all positive, so we have length should equal to positive value, because we are dealing with dimensions, right? So everything should be positive. You've never heard of anyone that says I am negative 5 feet tall. So it's always, positive in the length for any any length segment should be in positive. So we're going to need to restrict the domain for all of this. So we're going to make everything like kind of greater than 0, and we're going to solve and see what is the least restricted. So first of all, we got x greater than 0, so we got 9 minus 2x greater than 0, minus 9, we got negative 2x greater than negative 9, and then divide by negative 2, it will cause the sign to change. So we got x less than 4.5. That's one restriction. And then we're going to have the second one, solving it the same way, minus 5 from both sides and divide by negative 2. We should have x is less than 2.5. So we're going to choose so we got these three restrictions here. We got x has to be positive, but it has to be less than 2.5 or less than 4.5. And we're going to choose the least of the restrictions. So we're going to assume that it can only be less than that, 2.5. So we're going to combine it together. It got to be greater than 0, but less than 2.5. So this is where we're going to kind of limit our domain going to be. So that's the final restriction that we're going to choose. And then next, we're going to find the potential volume. So we're going to go back to this formula that we have earlier. Volume equals length times width times height. So I'm going to actually just show my work here. Volume equals length times width times height. and that's equal to the length, which is 9 minus 2x, the width is 5 minus 2x, and the height is x. And if you want to make it look nicer and just, rearrange everything, it doesn't really matter, but, just a matter of making it look a little cleaner. So we got, this is the formula. So what we're going to do now is I need you to go to your decimals. So go to your computer and open up decimals. And I need you to enter this equation. And you don't have to use v, just use y equals, and then the rest is x. That's fine. Just like how I put it right here. So I have previously already done that into decimals, and that's what I put in for the equation. And as soon as you finish typing, you may have to play with your mouse and zoom in and zoom out until you see we want to maximize the volume of this box, right? So therefore, we want to, and how does it play out as a polynomial function? It's basically a cubic function, right? So it's in the shape of an N. So as you can see, we talked about the minimum, maximum yesterday. So we are looking for the local maximum, which in this case, everyone, hopefully you can see that right there. And that point, I should have clicked the point on decimal, but if you place your cursor like right there on that point, you should be able to obtain the point. And it should give you like a value, like 1.03 something 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 comma, and then maximized is like 21, the value, the actual volume. So go ahead and do this in your decimals, and this tells you that the maximum here will give you the volume of 21 inches, cubic inches, of course. So the actual dimension that the length of x should be is approximately, so you have x is approximately 1.03 inches, which will give you a maximized volume of about 21 cubic inches. So to answer the question, we want to make sure we address the question. So the question is as to the nearest tenth, which means 1 decimal place, find the value of x that maximizes the volume of the box. So that's why we have the keyword maximize. So this is why we are looking for, in the picture, in the drawing, the maximum volume, which is going to be at 1 point, and the value of x is 1.03, and the maximum volume is 21 cubic inches. So that's how you would solve this using a polynomial function, and that's how it relates to a real-world problem. So now I'm going to have you actually just pause for a moment and think about what we just did, and we're going to have you try this problem because there's only 2 problems today for today's lesson. So you're actually going to try this one on your own. And this is pretty much the same exact thing that we just did earlier, except the numbers are going to be different. So then you can try the problem. So as you can see, the original here is length is 25 and the width is 13. So go ahead and try the problem. Hopefully you've had a chance to try the problem, and you should have used decimals to help you to obtain your polynomial function to get the maximum. So here we have the new length should be 25 minus the 2 edges, so it should be 25 minus 2x. And the width is also should be 13 minus 2x, correct? And the height should still be x. So we have the new length is 25 minus 2x. The new width is 13 minus 2x, and the new height is x. So the volume in this case should be x times 13 minus 2x times 25 minus 2x. But earlier I forgot to mention that we had a restriction earlier. So we need, let's go back to the previous problem for just a second. We had stated that the restriction for x value is between 2.0 and 2.5. So look at what our answer was. We found that the answer was 1.03, which falls right into the category of between 0 and 2.5. So that's how you can help yourself to get your answers restricted and kind of like, double check to see if you're in the right range. So we're going to kind of have to do that over here for this problem. So we've got all these three restrictions. Remember, they all need to be greater than 0 to start with, right? So we're going to solve the two that are up here. So here we have 13 minus 2x greater than 0. If you solve everything, you should have x less than 6.5. And then solving the second one, 25 minus 2x greater than 0, should give you an answer of x less than 12.5. And remember, we got to pick the least of the restrictions, so we're going to restrict it to the answer should be between the domain, in other words, is going to be restricted to between 0 and 6.5. And so using this is the equation, and with the restriction right here, we are going to use Desmos to help us obtain the equation. So go ahead and log into Desmos again and enter this equation. Again, use y instead of volume, instead of v. So use y equals x times that whole expression, enter it. And here is what I have. I already entered the equation. And here's what I have for the equation. And for this one, because again, we want to find the maximize volume, which means you need to look for the local maximum again. So you need to probably zoom into the graph towards the top. And this time I actually clicked the point that is on top, as you can see. So it is actually the point here on top gives me the length of the x value. So I have x, which is approximately 2.7, nearest tenth, so 1 decimal. And again, I believe this unit is inches. So that's our actual answer for the x value. And notice that it falls within our range right here of between 0 to 6.5. So we're going to be looking, basically this tells us we're going to be looking for the answer between 0 and 6.5. And there is the maximum right there. And so the maximized volume, we don't really need to look for it, but just for the sake of listing it, it's actually 402 cubic inches approximately. That's the maximized volume for these dimensions right here. And that's the end of the problem. Hopefully, you are now convinced that polynomials are connected to real-world situations. And let's take a look at the discussion question. Describe how the attributes of a polynomial function are determined from the function written in intercept form, and how information of these attributes is useful in drawings of the graph of the function. So, if we have a function in intercept form, which means like they're actually factors like this, you can actually set the equation equal to 0 and get the x-intercepts. So you got x-intercepts. It helps you get the x-intercepts, which tells you, which means, it tells you what the zeros are. So you got 0, x equals whatever it is. It helps you label where the graph touches the x-axis. So that is how you can, use that to help you draw the graph of the function. So hopefully you are now confident to draw any types of polynomial function given these attributes and what you have learned about increasing, decreasing, positive, negative, using your maximum or minimum, global or local, tangent or crosses to conclude and have confidence in drawing the complete graph of what a function should look like even without the graphing calculator. And that's basically the end of lesson 5.4. So you are now going to get started with your last assignment for this lesson, day 4, and go ahead and log into your Google Classroom and get started with your assignment. And have a nice day.